Hi, math lovers. Today we're going to work on notes number 46, lesson 2.3. We're going to talk about parent functions. So in your textbook on page 216, I want you to look at the parent functions. Now this is the graph of all of the functions without anything fancy added to them. We've got a constant function. Notice how it doesn't change at all. We have the identity function where f of x and x have the exact same value. We've got the absolute value function, which takes the identity function and flips all the negatives and makes them positive. So we have a nice V shape. We have the square root function, which we've done a bunch of already in our last chapter. The quadratic, which gives us a nice parabola. Notice how similar the absolute value function and the quadratic function are. Notice that the endpoints are the same. The end direction, the end behavior is the same, because if x is positive, then x squared is going to be positive. And if x is negative, then x squared will also be positive, same as in the absolute value function. The cubic function is a nice S-curve. Notice that the end behaviors are different. The reciprocal function, notice we have no defined value here where x is equal to 0. So we notice the graph does not cross 0 at all. And the last one's called the greatest integer function. This is probably the newest one for you to see today. The greatest integer function means as you move from left to the right on the number line, what was the last integer that you passed? So the greatest integer. All right, so be sure to check those out. Maybe you want to make that your screensaver. Take a nice picture, make it your screensaver on your computer, or your take a nice photo of it and make it your background on your phone. All right. So the first one we're going to pull off today is number 13, and they're saying here write a linear function such that the indicated values are given. So f of 5 is -4 and f of -2 is 17. So they're telling me it's a linear function. So do you know what it means to be a linear function? That's right, it's a line. So I have the point 5, -4, and I have the point -2, 17. All right, so here all I've done is same thing from the last couple sections. I'm giving you 2 points. Find the equation of the line through 2 points. So of course you're going right to your slope, which would be 17 minus -4 over -2 minus 5. And that's going to be 21 over -7, which is -3. All right, so I have the slope and I'm given 2 points. What formula do you want to use? Point slope. Very good. So let's pick a point to use. So we use y minus, how about we use the first one? Y minus -4 is equal to our slope, which is m, -3, times the quantity, x minus x1, which would be 5. Great. So we can just clean that up. So y plus 4 equals -3x plus 15. And let's bring our 4 over. So y is equal to -3x plus 11. Now, this is the equation of the line. They asked me to give it in function notation, so I'm going to change it to f of x is equal to -3x plus 11. And there's my function, okay? Not tough at all. Number 43 asked me to figure out what these values of x would be, 2.1, 2.9, -3.1, and 7/2, if we put it into the greatest integer function. So what I'd like you to visualize is the number line, okay? So think about the placement of these numbers on the number line. So I'm just going to throw a number line up there. As you move from left to the right along the number line, what is the last integer you passed? So I've got 2.1. So let's make this 2.1. 2.1 is between 2 and it's between 3. So as I move to get to this coordinate on the number line, as I move, what was the last integer I passed to get to 2.1? That would be 2. 2.9, here I am at 2.9. What was the last integer I passed to get here? Well, that would be 2. Oh, mixing it up now, -3.1. That is between -4 and, -4 and 3, -3. So here we are at -3.1. As I move along the number line, what was the last integer I passed? -4. How about 7/2? Oh, mixing it up here with the fraction, right? 3.5 is over here, 7/2. That would be between 3 and 4. So the greatest integer would be 3. Okay? As long as you visualize the number line moving left to right, you should be good with those. I've got another one here, another greatest integer function, number 49. They're asking me to find g of negative 2.7. I'm going to pick a negative one for us to do together, since sometimes the kids mess up on the negatives. They get a little tricky. So let's go ahead and put negative 2.7 in for x in our function. So it's 3 times the greatest integer function of negative 2.7 minus 2 plus 5. Now, if you wanted to, you could just type this whole thing into your handy dandy. I'm sure you'll find the greatest integer function on your calculator. But, you know, I'm old school, vintage. I'd like to be a classic. What we're going to do is we're going to go ahead and work with these just like they're parentheses. So this would be negative 4.7. All right. Now, I'm ready to use my greatest integer function. As I move along the number line, I'm at negative 4.7. What was the last integer I passed? So that would be negative 5. So it's 3 times negative 5 plus 5. So that's negative 15 plus 5. That gives me negative 10. Okay, so that's kind of fun, something new. The last thing we want to work on here is what's called as a piecewise function. And piecewise functions take a little bit of one function and a little bit of another, and they put them together. I think that kids have trouble with piecewise function only because of the order that we give it in. When we think about things, we think about them in terms of if-thens. And that's how we do our computer science programming. We would say if the value is less than 0, then we want to use this function. If the value is greater than or equal to 0, then use this function. But when we give a piecewise function in algebra, we say it backwards. We say use this function if x is less than 0, and use this function if x is greater than or equal to 0. So what I'd like you to do is I'd like you to think about each function separately. Okay? So first, let's graph 2x plus 3. Well, that's a y-intercept of 3. My slope is going to go up 2 over 1, up 2 over 1, and there's my line. I'm going to think about the graph of f of x is equal to, how about I write it as negative x plus 3. Right, you're back up here at positive 3 for a y-intercept. Your slope is negative, so down 1 over 1, down 1 over 1. So this is going to be a line like this. So what it's saying to me is use this first graph when x is less than 0. So we want to use this part of the graph. And use this graph when x is greater than or equal to 0. So you're going to use this part of the graph. And what I'm going to do is I'm going to take this part, I'm going to take this part, and I'm going to stick them together. So let's see, 1, 2, 3, and then I go down 2 over 1. So here's this line. Uh-oh, I made a problem. I made a solid point. What should it be? It should be an open point, shouldn't it? But no fear, because over here, down 1 over 1, down 1 over 1, the line is going to go like this. The two piecewise functions actually land on the same point. So my graph would be this one. If you look in your textbook at example 3, notice they have a piecewise function right here that does not line up. Okay, they don't share a common endpoint. So we have one open point. We have the open point where it's greater than, and a solid point where it's less than or equal to. So be very careful with that. Okay. All right, so we covered a couple different things. We found a linear equation given in function notation. We worked with the greatest integer function. We talked about all your parent graphs, and we worked with a piecewise function. Have fun on your problem set.